Welcome to the Intellectual Anarchy podcast. I'm Patrick Sullivan.
And I'm Catherine Cruz, and I'm just a curious cat.
The way we learn is a very multidimensional thing. And the way we learn to put together what we learn, likewise, is not just a linear thing. So years ago, the country, and you see this in Hawaii, it's kind of like people aspire to be white-collar jobs from blue-collar jobs. So a blue-collar job is somebody that runs a factory. And for example, at UH, in the College of Engineering, what used to be, and I haven't checked this lately, but to use the shop, you make a drawing, you go do these things. You go to a window and you talk to a guy behind the window and he goes and does it for you. Contrast this now with at Stanford, everybody can use the shop. So what happens is people experiment and they try things. They get a safety class because here the argument is, well, it's not safe. But what happens is people don't learn how to actually make stuff. They don't learn to learn with their hands. And as a country, as a society, for a long time, we dismissed that because that was like dirty work. And it's kind of interesting because, for example, I've got a bunch of stories like this, but this one was interesting because there was I was building a gate at the house, and I had done a design. And so I found this guy. He was like it must have been an 85-year-old Japanese welder. A little Japanese guy. Now the pipe, everything is heavy and you got to bend it to make it, the top was kind of curved and it had these lines. It was very intricate. And this guy pulls up with a truck and he does it all by hand because he learned this working on the plantation, the skill and the art of bending metal without machines. And I mean, it was artistic. It was something to watch because he couldn't even carry couldn't carry the pipe. He's too small and he's old. And yet he's moving the pipe and he's making these very nice designs. So the science of making things differently, because the way I think about it is, well, you have machines that'll bend metal, so go get a machine. But see, you don't understand the knowledge and the innovation that comes from the skill of actually being able to do things. And so what's happening today is this loop between making stuff, trying things, turning the design, and building things. And of course, today you have 3D printers, you have shops, you have all kinds of stuff. But we kind of lost our edge in that stuff, and we ceded manufacturing to everybody else because manufacturing was like a dirty job. Parts of it clearly are really hard and difficult work, but there's a real value to how we learn and doing things with our hands. And so in this chapter on hands-on innovation is to really speak to this issue of how we learn versus on a piece of paper it says you should do these things. And some people are not good at following the paper, but intuitively they can just do it with their hands. They kind of know. They have a feeling for it. And I have some examples I talk about in the book. There's ways of learning, encouraging a radical experimentation, the second bullet. We do that here a lot. Like, let's make something. Even if it's crappy, we'll learn, right? Make it better next time. But you learn so much faster by iterating through it versus saying, I don't want to touch anything until I exactly know everything and all the answers, because sometimes you won't know the answer until you get your hands on it.
Yeah, hurry up and break it because you need to
Exactly.
fix it and create something.
And I mention, I know in the chapter I talk about Paul McCartney, who doesn't read music, but who's been prolific at creating music. And if you just went by kind of traditional book learning, you would dismiss him and say, well, you can't do this. And yet learning on paper is one way to do it. But actually learning with your hands is also legitimate. And so that's essentially what he's done, is learns with his hands and his ears. And so I think as a country, we don't give enough credit to that. And so that's what making stuff is about. And for us here at Oceanit, it's made a huge difference, getting people comfortable doing things like that without judging them. Now, some people, they're just going to hurt themselves. So you've always got to be careful of that. But others, it's like, let's try something. And you try it, you make it better, you do it again, you iterate a few times until you get, wow, okay, that's really good. Sometimes that's faster than trying to do it all on paper. So there's a lot to learn from actually making things. Comment too about Elon Musk with his heavy lift rocket, and he launches them and they blow up, and launches it and it blows up, but each time he's learning. Whereas I think NASA's gone after it like, we can't fail, can't blow up, can't do anything, because it just looks bad or whatever it is. So it costs them a ton of money, takes a lot more time. Whereas by just trying it and blowing it up and trying it and failing, he's learning how to get it right much faster. That's what we do here, and that's what we need to encourage more people to do.
Are we not doing enough of that, you think, in the schools?
Absolutely.
Yeah.
I think we discourage people from making things as though it's below them when it isn't. And so appreciating even the trades, carpentry, plumbing, welding, the people that do those things and do it well, even if you try it and what you do is kind of crappy, if you get somebody that's got the skill and you kind of show them what you're trying to get to, they can make it better faster. But there's a huge value to that, because you're going to get to something that really works. Once you get something that works, you can make a machine make it. You can do all kinds of things with artificial intelligence, but the human element of working with your hands is still really important.
Well, I had just talked to a tenor from Tonga who went back home, and he played with the student orchestra, and he said, it's tough over there, because when your string breaks, you can't just go to a store and buy the string. And so the kids are having to weave the string, to play music.
Right. And they're learning something.
Yeah.
And so learning by doing and learning with hands is critically important, and something that we need to encourage people to get comfortable with. Because if people only wear a suit and sit back and point to people and tell them what to do, you lose a lot in the translation. And so the people that are really innovative kind of do both. You can write it on paper, but they can actually get their hands on it and try it. And they can play with models and things to give them insight. And so one of the interesting stories is Richard Feynman, who got the Nobel Prize in physics, was looking at rotating plates and had some interesting ideas about quantum mechanics. Going from one field to the next, trying something, integrating that into something else helps clarify the theory about how something else may work. So there's a real value to getting your hands on stuff. And we try really hard to make that available here. So we have all kinds of equipment and gear for all kinds of things. You can make, my thought is you can make anything you want. But you can't just sit around and look at, each other. It's like, try and make something. So the nano surfboard that I talk about in the book is a surfboard that has titanium nanotubes. And back then, we were looking at nanotechnology is a really cool field, but we weren't making things. Mostly just had PowerPoints, we're reading things, we're talking about stuff. When we made that surfboard, which was an expensive surfboard with titanium nanotubes, which makes it more ding resistant, turns out it's quite ding resistant, we learned not to be afraid of doing things with nanotechnology. And that opened up an entire area of making things in nano, which became what we do now in industrial nanotechnology manufacturing. But it was because we broke through that ceiling and people became unafraid. And afraid maybe isn't the right term. Nobody wants to look stupid. It's kind of like, we're going to try something. It may look pretty funky, maybe the first iteration, but let's try to make a surfboard. We can agree that a better surfboard makes up for a better world.
I guess when I think of, Duke and the Hawaiians that created surfing, right? And
Absolutely.
you use a piece of wood.
Absolutely.
And you jump on the wave and you try it,
Right.
And then, just this morning I was out swimming and there was a guy on a foil board, and I'm just thinking, gosh, it's just amazing how, we've been able to transform that sport in so many different ways.
Yeah. Just making stuff, trying it, redoing it, trying it again, trying it differently, trying different combinations. It's a valid way to learn. It's underappreciated, and people are discouraged from it in school. And so my thought is, kids need to be encouraged to try that. And sometimes when kids get stuck, you can unstuck them by changing the way they're learning. And by that I mean, when they're trying to get it on paper and you can turn it into something they can touch and feel, sometimes the learning changes. And
It's a good update.
What did you find?
That's kind of scary.
But an example, and I talk about it in the book, but when my daughter was in high school, the teacher said she's struggling in math. And so what I did was I took away all the paper and pencil and stuff, and I just went to the cupboard. This is when she was pretty little, with cans and things. And it was just moving cans and things around on a table to get a feeling for math. And once she got the feeling for math, it all changed. But you're connecting different parts of the brain and learning in different ways. And then once you do, you connect other things, and then it just accelerates. So she later, as I mentioned in the book, got her PhD in engineering. Doesn't have a problem with math at all. But see, the teachers at the time said, she's struggling. I don't know if she can do this. And I'm thinking, I don't get it. So the experiment in changing the modality of communication with math made math real and intuitive and easier. But if you only did it on paper and you could only do it with a pencil, you lose what it really means.
Well, you showed her a different way to look at math.
Exactly.
Yeah. I mean, I think of when my daughter was small and she was pretty good at math, and we have a big pool table downstairs, and she was, it's all about geometry, right?
Exactly.
And she picked up the triangle and she was like, you think I can fit through this? And I'm like, who thinks of stuff like that? And she did, and she tried it and she fit through it, and I was like, wow. But, just looking at things differently.
Yeah. And so that's part of learning. And I think, again, we need to encourage it. And the people that do that become, in my opinion, much better engineers and scientists, because they spend all this time learning theory, but they're not afraid to do practical things. And when you're stuck, sometimes making something practical informs the theory, and vice versa. So there's different ways to innovate, and there's different ways to do things, but you can't exclude the universe of how people learn because of some parochial idea you have about how learning is supposed to be and how education is supposed to be. Because, again, we look at education as there for the convenience of teaching, not necessarily for the best learning. Mm-hmm. Everybody learns a little different. And so trying to find a way where they do learn and it connects, once it connects, it's kind of an indelible connection. It's like they just get it. Once they get it, then it's kind of like you can't stop them. But when you tell a kid, because he can't do it on paper, that there's something wrong, they start believing that. And that's a tragedy.
I think of the professor up at the University of Hawaii, Yana, who he had his lab in a pretty dilapidated building, but he had the students work in the lab, and they came up with the gene that makes starfish kind of glow in the
Right.
dark, right? And he
Right.
transferred that to the mice, so he had glow in the dark mice. And then, of course, after that breakthrough, he got a very nice lab. But he didn't wait for a nice lab to
Right.
create something. He just had very
Right.
modest, surroundings, and he just tried it.
Yeah, and that is the attitude people need to have. Because again, having a beautiful lab doesn't mean you're going to do that. As a matter of fact, I was talking to some friends of mine at Rice University and the group so there's a group there, they got the Nobel Prize, Smalley got the Nobel Prize in carbon nanotubes a few years ago. And so I was talking to the guy that runs the Smalley Institute. And it was interesting because he said back then they didn't have very good labs. Back then everybody had to share. And sharing space and bumping into each other, of course, sometimes was inconvenient, but it created all these conversations. They were really innovative because it wasn't a beautiful lab. It was a very connected environment with all kinds of labs and people from different fields trying to use equipment in space. And he said, now we have all this money. We have beautiful labs. We just can't seem to innovate anymore. And I think it's an important lesson and kind of instructive. And I tell people here, and that's why our labs are so overcrowded. But what it does is you bang into people, you share ideas by virtue of the fact that you're in proximity and you see what they're doing. You can talk about it. You can, for example, we're doing a interesting project in biologic computation, which looks like could be more efficient and faster than even quantum computing. So the way to think about it is your brain is a biologic computer. So you've got this synthesis going on as you're thinking. And so we're trying to come up with a way to do computation with organic molecules to actually produce outcomes and answers. And we had bought, this is really kind of what happened, we had bought this machine, like a $100,000 machine, and the next day then we hacked it and validated the warranty and set it up to do this computation. But what's really interesting is that for the kinds of biologic computation we're doing, it would take you years otherwise. And we can do this, like in hours. We're trying to mimic what we think is going on in other biologic systems because it's efficient, but it's a different way to do computation. But that's in the lab downstairs next to the guys doing work on batteries, next to the people doing work on lasers, and and so all of this is kind of going on in proximity. But it's a biologic system doing computation, which is not what normal people think about. And the system is built for synthesis. It's not built for computation. But we just took it over and changed the software.
So you have all these people playing in the sandbox, and they say, oh, yeah, how's it going? And they're like, I've got this problem. And then you get another set of eyes, and they're like, why don't you try that? So it's that kind of synergy you work off of.
It is, and it cuts across fields and disciplines. It's a different way to think and do things, and so you're kind of sharing it. But it's an innovation-rich environment. When everybody has, again, their beautiful antiseptic labs and they don't talk to anybody else, they just do what they do. So they got the beautiful lab, but they're not suffering the sharing a coffee machine or, the kind of things that would have them talking and collaborating.
Right.
But he was telling me the story, again, this guy at Rice, that one guy in the labs had this observation, and then he had talked to this other guy, a physics guy, about what might be happening. And then, banged into a chemistry guy, and they just started kind of talking, and they came up with some ideas and a theory. And then the guy says, well, let me try that, and became the basis of some experiments that turned into a Nobel Prize.
So then where else do you take the nanotechnology, from the surfboard to,
Oh,
I don't know.
in our case, clearly, well, the energy space. So we can make energy systems way more efficient with nanotechnology. Medical. We can not only produce tests, therapies, we can build delivery systems. So we've got a thing called a nanovector. It's a nano machine we build, but it'll deliver a payload on a tumor. So we did this on rats for certain kinds of tumors. You can use it for beauty products. You can use it for so many things. So it's a fundamental foundational technology, and we've been using it in all the above: healthcare, aerospace, industrial applications, energy applications. So at Oceanit, after the surfboard, it was all of this cool stuff we can do. And then it's kind of picking the things we want to try. And we're still doing that today. I mean, we're literally still trying stuff today. But that's why finding something that we think is, interesting and important, and then trying it out, making something, even the nano surfboard, all of a sudden it's like, hey, we can do that. What if we mix this and this? Okay, what if I apply it over on this problem? Okay, what if I can do this thing? So for example, one of the things I mentioned, a beauty product, we built a manufacturing technology for this nanomaterial here in the basement. Now we're teaching a group in South Korea how to manufacture. But we actually started it in the basement, and we are literally training them on how to manufacture because they don't know how to do it. Now we don't know beauty products, that's their business, but we know about nanotechnology. So we're able to scale it as well.
I'd always heard that, we come up with these great ideas, and then, another country swoops in and takes that and then, builds on that. So that's the...
And to some degree that's true because the world is connected. And universities and national labs are good at their original science. They're pretty lousy at scaling and manufacturing. But the things that are really disruptive, it's hard for them to translate that to normal people on the manufacturing side. What we've managed to do is both. So we literally go from the science to scale up. The reason that's critical is because a lot of the scale up has never been done either. And if you try to make it like something you already know, it turns out it won't work.
So if you've got a little bit of ingenuity and then you feed that.
Right. And back to the hands-on thing, because you not only then are doing the theory, but you're not afraid to take it to scale. You're not afraid to think of scale in big machines. A lot of people just do one or the other, but they don't do both. But what we've done is created a safe place where that's okay. And it's kind of interesting because not many people do that, but we not only make it okay, we encourage it. And we have people that have different kinds of skill sets. So we say from a notebook culture to a documentation culture. In a documentation culture, you've got traceability, quality systems, and all those things. People will help out with that. The lab people with the notebook culture don't like the documentation culture, but they also know why it's important. So they collaborate. So you have people that will reach across these cultural, differences and work together to create that documentation. So now I can produce it in replicate samples at scale. That's how that happens. But we've created a connection between those two cultures. And so it's not so much that they have to be experts on everything. They have to be experts in something, but they mostly have to appreciate other people's expertise. Back to this thing about making things. I can do carpentry, but I appreciate a skilled carpenter because the guys that do that are artisans. And I'm not that good. But I know how to make stuff, and I'm not afraid to make stuff, but I know the difference between what they do, which is something to, behold, versus something that I do, which is just functional. But see, I understand the difference, and I appreciate what they bring to the table. And that's what I try to encourage our folks to do. So when they find those craftsmen welders and others that are going to make stuff, they work with them because what they do is hard to do. It's a skill. It's about repetition and practice. They're a critical part of the whole system. So we need those craftsmen. And we need people that want to do that. So we need everybody to work together.
So when you think of McCartney, you know, and his skill and his creativity, just because he didn't read music, wasn't a barrier.
Right. But had he just listened to a couple teachers say, you can't do this, maybe we wouldn't have the Beatles.
But he had the passion.
But he had the passion, he had the drive, and he wasn't going to let that stop him. And that's the thing, is trying to encourage people that have these gifts to keep going with it, even if the gift is different than what everybody thinks it should be. And that goes back to people that are just good with their hands. It's a gift. And they should embrace it. They shouldn't be ashamed of it like they're getting their hands dirty, because if you don't do that, you can't make stuff. And we all know that. But they're a really important part of the ecosystem. And to encourage people to learn with everything that they can, that is something we should be encouraging.
So it sounds like you've got lots of fingers in the pie. I guess just looking back, at all the things that you've tried and the successes, I don't know, are there particular areas that you feel particularly proud of?
There's a whole bunch.
Yeah.
I think, this rapid test that we just put out.
For COVID, yes.
For COVID, it went from a theory. And the early theory we were looking at sounded wacky, causality in biology, like, is there math involved in why people get disease? Which is still a good question. We don't have all the answers, but we created a tool set because we asked that question. That enabled us to design molecules with we call a grammar of RNA. RNA being one of the key building blocks. Getting that test out, the team went from the science to putting together an entire manufacturing system, clinical studies, everything. So they went from the theory all the way to a product that works really well.
I thought it was an incredibly exciting time. I mean, it was a terrible time when we had, to deal with the pandemic and people were dying. But the fact that you had some of the sharpest minds, across the country, across the world, really looking to say, okay, how do we find this solution?
Right.
Yeah, that was pretty amazing.
And the mRNA vaccine that really was a big deal never would have been used the way it's used today, except for COVID.
Right.
Because that totally changed the way you design it. And so the idea, the science was around, organizations like DARPA had invested in these early ideas, but COVID created an opportunity to get people to think differently about how to create vaccines. And now the same delivery system, the mRNA delivery system, can be used for fighting cancer, for all kinds of things. Before that, it would be too risky. Now it's not a problem. And the negative impact and implications from that vaccine are so minimal compared to what we do today, and it's so much more effective than anything we've ever done. So, it's really remarkable. But the pandemic created those opportunities. So in our case, since we were working on this problem of the mathematics of disease and understanding genetics and DNA and RNA, we thought, well, let's try to do something useful.
Yeah, so then the next pandemic that comes along, people can stop and say, okay, how do we
But what we're doing now is we're actually trying to take the tool set and look at creating therapies for different kinds of diseases, in particular cancer. So we are literally launching several programs to look at different kinds of cancer with the tool set we produced.
Okay, so not just waiting for the next pandemic.
No, not at all. And with the knowledge we gained from making that test, we're now applying some of those ideas to things that are never been solved. But because we have the tool set and the understanding and that success under our belt, there's a lot more confidence that we can do it. So we just put in I think it was a proposal yesterday to work with the university and others on a bunch of clinical work, but we can actually build those things here because we built the tools.
I just learned something about CAR T cells, and they can treat blood cancers, and it's been pretty successful using your own blood and reworking, the cells, and then
The technology for this
it's
stuff is
amazing.
just really impressive, and it's only getting, in many, many ways, it's getting better. I mean, we're learning that the complexity of disease in the human body is more than we thought. On the other hand, the tools we're building are much better, and the kinds of things we can do, we're still imagining new ways to use the old tools. The more recent ones like CRISPR, other things where we can go in and snip out a piece of DNA or add another piece of DNA. There's all kinds of things that we can do. Learning how to do that more efficiently and more effectively, that's going on right now. But the old paradigm and the idea that we don't have any options, that's not true. The real question is, can we do it fast enough? Can we make things and test them? And we got to do a bunch of that. Try it, test it, see what works.
Yeah, because it seems it's pretty. Whoop, pause. I think that's my phone now. Okay, my other phone. Yeah, so it just seems like we're in pretty exciting times. When you think of like the Industrial Revolution and all the factories that developed after that.
Well, it's funny you say that, because let me just move this piece of paper here. It's funny you say that, because for a decade or two after the beginning of the internet, we were mostly building apps, pizza apps, car ride apps, apps for all kinds of things. Now we're back to building real technology, machines and devices and systems and things, using new ways to manufacture, new kinds of materials, new ways to use materials, and the opportunity space is huge. So the world has kind of moved in that direction now of literally making things versus just building apps. Clearly, AI is got all kinds of applications, but AI in service of manufacturing and making things. But those things that are made, for example, we're doing this thing right now on space armor. So it's using biomimetics, which is the imitation of biology, in this case, like seashells and other things, to inform a design that's mathematically optimized using AI to take hypersonic impact. So space debris, for example, things in outer space. If you're in outer space and there's so much junk up there, you're going to get hit by debris. Debris is moving really fast. So chances are, if you're just wearing a suit, maybe even just a space capsule, you might get a bunch of damage. The nice thing with this is that if you can take a Mach 5 or Mach 6 impact on something that's very light, it can only be printed. You can't pour it. It's a new way to make materials. You could do pretty well surviving. So we're literally in the middle of that project right now. But what's interesting is it's biomimetics, meaning learning from nature to inform design. We're using, and we've got all kinds of materials we're using. So materials that exist today and materials that don't exist, we kind of refer to as unobtainium. Things that aren't available on the planet, but we can make them anyway because we come up with new ideas. And then the other thing that's kind of interesting is that we're looking at treating old materials with surface treatments like nanotechnology. So all these new things are going on at one time. So it's a very exciting time. Again, the vast opportunity space for outer space, for inner space, for medical, for energy systems.
Yeah, no, that is pretty amazing when you think what's possible.
Right. And so the application of imagination to imagine something in a different way, that's going on. And that's why I mentioned biomimetics. It's a really fascinating field because, again, nature has perfected these designs through evolution of millions of years. Humans are learning how to learn from nature. That hasn't happened like this in a long time. And then using that knowledge to create new things that otherwise weren't even thinkable. And that, again, has vast applications. So it is an exciting time.
Yeah. So you think about making a better mousetrap.
Making a better world.
Yeah.
Absolutely. So everything from national security to healthcare, recreation, entertainment, space travel, extending human life, improving the quality of life, enabling people with disabilities to have more full range of things, from people that are paralyzed to people that maybe lost a limb. There's all kinds of stuff going on. And so the possibilities are vast.
Yeah. The quality of life.
Absolutely. That is a valuable thing too. And so in spite of the fact there's a lot of troubling things in the world, you've got some wars going on, you've got things that are really bothersome. But at the same time, technology is moving the world forward. It's going to change a lot of things. It's already started.
Yeah. That's pretty amazing stuff.
Yeah, and so what the U.S., I think, needs to do is to unlock the potential of this human capital to innovate a better world. And by doing that, maybe change the calculus of war and the incentives people have to do those things. They're kind of changing the terms of what's really valuable and important. So all of that is in front of us. So it's quite exciting.